Hello guys, thank you for this opportunity to give a talk about visual servoing. Let me give a brief introduction on myself. You can find me from ResearchGate, and you just need to search my name, Bo Shang. So from here you can see what I have done around UAV path planning, and after that I did something about UAV visual servoing. You can find all of my research articles. And this one is the most cited fractional order robust visual servoing control of a quadrilateral UAV with larger sampling period. From this article, you can see what I have done around drone visual servoing. First, let me introduce the platform we use. It is a drone platform. Like here in the middle. It is a 3DR DIY platform. And then we added a Odroid. On the Odroid, we connected the autopilot with a TTL to USB port. And then we added a camera to the Odroid, a Wi-Fi dongle. And then we can use a laptop to connect to a Wi-Fi hotspot. And then the drone connect to the same Wi-Fi hotspot. And this way we can use the laptop to monitor what is happening on the drone, as well as see the video from the camera on the drone. Let me show the video what I took. I have made a YouTube playlist for the drone visual servoing. First go to my channel. And then we have this playlist. So the first one is about the real drone, the 3DR DIY platform. After the drone is connected to the laptop, we can log into the drone via Wi-Fi. And then I'm going to fast forward this video. We run a Python script from the drone. And that Python script contains commands to process the video and control the drone to track the target. From this web page, if we enter the address like this, we can see the video from the drone. It is also included in the Python script. If the target is detected, we can see a circle. Now it's using the initial threshold. We can see the drone is taking off from the ground, and the red circle is the target. Now the target is not detected because the parameter needs to be tuned. When I do the experiment, I need to retune the parameters each time because as time goes, the sun changes its direction, and then the parameters need to be changed. Now you see the red circle can be detected better, but it is not good enough. So I retuned that with this small app from the browser. You see here, the red circle can be detected better. It's more stable. But you can still see this page refreshes at the frequency like 1 Hertz. You see it's a very low frequency. And if you check the message from the terminal, you can see sometimes it says object found, but sometimes it doesn't. The object found frequency is a little higher than the refresh period from the browser, but it is also not good enough. So this is what we did on the experiment side. From this experiment, we can have the following results. We know that the challenges of drone video servoing is like this. First, image processing technique is always sensitive to light condition. You may think the word always is very absolute, but I think it is really the real case. The image processing technique can work in some restricted area, but if we want to detect and following something in real sunlight, it is really difficult, and we often lose the target. So this is the first challenge for drone video servoing, especially when we do something outside. And the second one is sampling period. The sampling period is often large. For a drone that is acceptable for most industry, the drone should be a limited system. That means the price should be limited, the weight, the volume. The drone cannot be too large, and the battery volume. So from all of that, on a drone, we only have a limited computing resource. In this way, we often have a large sampling period on a drone. This is a challenge for the drone video servoing control. But those 2 points are not from the control side. From the control side, we can think of specific controllers that can deal with the large sampling period or the period variation. For us, we have tried to use the fractional order controller. And We have already showed that fractional autocontroller has some benefits in large sampling period. And then we want to think this is not good enough, and the drone video serving really needs to be improved. But how to improve that? We need to, or the community needs to do more experiments. But doing that kind of experiments is not convenient. It really takes a lot of time to prepare the drone, wait for the good condition, that we cannot let the outside has too large wind, because the camera view is limited. If the wind is too large, then the target will go away from the camera view, so we cannot detect and follow the target. And it really takes a lot of time to do those kind of experiment. So what we tried next? We thought to use a platform that can do those kind of experiments indoors. In this way, we went to the second video. We used the platform called AR drone. In this video, we only showed AR drone heading control. That means if we use the mouse to click some target, then the image processing technique can focus on that target, even if the drone goes forward, backward. And then when the target moves, the drone can make itself, can focus itself, change its headings to just head to that target. You can see the drone goes forward, backward, but the heading is always to the target. So this is a small video to demo the drone video serving using AR drone. But how do we comment the AR drone platform? The AR drone platform is better and easier to use. It can provide a higher frequency of the video transmission. But it has some disadvantages. That is, the AR drone platform, it's hard to add additional sensors and apps on board. We can only add controllers on ground control station. So we want to seek some platform that can be easily to use and test the drone video serving techniques. And then we changed to a simulation platform, that is Gazebo and MATLAB. Then we should go to the third video. This is the third video. We have made use of the system called ERLE robot. In that system, coworkers have prepared a platform in Gazebo that has a autopilot. That means a quadrotor drone can fly in a Gazebo environment. Because it is Gazebo, so it supports the ROS. That means robotics operating system. So if we prepare a controller that can support the Marlink message, that means we can interact with that drone in Gazebo. So we prepared a Simulink model that can read the Simulink message from the drone in Gazebo, and we can get the image processing result from the Gazebo. And then the MATLAB model can output the controller result back to the Gazebo environment. So the drone can be controlled from our Simulink model. Let's go forward and see what can we do. You can see here, the target can be detected by the image processing technique. And then if we keep going forward, we have set the upper limit and the lower limit. From this screen, you can see sometimes the target is not detected. So the image processing is also unstable in this environment, which is really similar to the real experiment result. Now you see the drone can move itself just above the target. And you can see from the left bottom, I'm trying to use my mouse to move the target. And then the drone just move itself following that target. I think that's all what I want to say. And there's also limitations for this platform. That is, your robot can only work on Ubuntu 14. And MATLAB is using something in Ubuntu 14 that is unstable. If we want to solve this problem, we can put MATLAB on another computer that doesn't use Ubuntu 14. And we use the internet connection to connect those two hosts. I think that's all for my talk about the drone wheel serving. Thank you for watching.